while explaining the matrix game, we have actually given two examples, and in one of those cases, the PSNE did exist, and the other case PSNE did not exist. Now, have you noticed something interesting between these two games, where PSNE exists and does not exist, and the fact that Maxmin and minmax were equal or unequal? Let me give you the hint. So in the first case, the penalty shootout game, we had this situation where the min-max value was equal to 1, which was of course greater than or equal to, and in this case it was strictly greater than the min-max, the max-min value, which was -1. Now these are not equal, but in the other case, the max-min value and min-max value both were equal to 1. And in that case, PSNE existed. Is this just a coincidence? We'll show in this module that is not a coincidence. Indeed, if you have to have a PSNE, if the PSNE has to exist, then it better be the case that this min-max and the max-min value be the same. Now, to prove that, let us also develop a little bit of notation. So first thing is that we are defining the max-min strategy of player 1, and this is just the strategy for player 1, which is argmax over this minima. So this is the formal definition, looking at the minimizing strategy. So for a specific strategy S1, what is the minimum value, and then which strategy maximizes that strategy we are going to call the max-min strategy for player 1. It's in some sense is the safest strategy or the worst case optimal strategy for player 1. And similarly, because we are using the same utility function, which is negative, the utility for player 2 is going to be the negative of that, then the similar notion of max-min for player 2 will be min-max in this context for player 2. So the min-max strategy of player 2 is something that we are going to denote with S2 star. So this is the min-max strategy for player 2. So here is the theorem which formally states, which we have just said earlier. So a matrix game U has a PSNE or a saddle point if and only if this min-max and the max-min value are equal, and this S1 star, and that equals the value of this matrix at S1 star and S2 star, where S1 star and S2 star are the max-min and the min-max strategies for players 1 and 2 respectively. And not only that, in particular, this particular strategy profile is going to be the PSNE, a PSNE of this game. So in order to prove this, we'll because this is a necessary and sufficient condition, so we'll do both directions one by one. So first look at the only if direction. So this is the only if, that is, we start with a PSNE and we show that this condition holds, right? So we'll start that this game has a PSNE, and we'll show that this equality is true. So suppose this PSNE is S1 star, S2 star. I mean, don't really need to be the same S1 star, S2 star. It will happen to be the same, but for simplicity, we are using the same notation that we have used in the previous modules. So by the definition of PSNE, what we know that this inequality holds for player 1, and we also know that the other inequality holds for player 2. Of course, because this is looking at U, then in that case the inequality will get flipped, but that will also hold for all S2. So a similar inequality you can write even for player 2. So let us start with this one. So because this is this is greater than that, we can actually, so this inequality is true for all S1 in capital S1. So we can actually write this even for the maximum value of this inequality is going to hold. In fact, in that case, it is going to be equal, but let us use the same argument, and we are using just this inequality, and we are taking the maximum. All right, because this is maxima, and because S2 star is a specific strategy, therefore we can clearly write using the definition of minima that we can say that this quantity, which is which is a fixed quantity only dependent on S2 star, because it is no longer dependent on T1. We have already taken the max. So this is going to be at least as much as the minimum. So minimum will always be less than or equal to that number. So we can write this min-max value here. So and if you write it in this way, we know that this is the min-max value of this matrix game. Okay, so now we are using the same argument for player 2. So you can write an equivalent expression. So what will that be? It will be S1 star, S2 star. That is going to be less than or equal to U of S1 star comma S2, and that will hold for all S2 in capital S2. And then you can use the same thing, but now the inequalities are flipped, and you are going to use first the minimum value and then the max, and therefore you will have the max mean, which is going to be larger than that. So this is the max mean. You can just redo the steps. The max mean value will be at least as much as the utility of S1 U of S1 star S2 star, which is the same value here. Now what do we see? So we know that V upper bar is actually at least as much as V lower bar, but here we have already shown that this is greater than or equal to the number S1 star U of S1 star S2 star, and it is also upper bounded by the same number U of S1 star comma S2 star. So this is these two numbers are actually sandwiched between those two things. So this is by the previous lemma, and this is what we have just shown. Therefore these two numbers must be equal to must be the same, and they must be equal to this U of S1 star comma S2 star. And that is exactly what we wanted to show. This S1 star and S2 star are going to be this. So this is if it is a saddle point, then these two things are actually going to be the same. And because these min-max values and so these S1 stars and S2 stars are nothing but the saddle points, they are also going to be the min-max and the max-min values. Okay, so so that implication of max-min value is just coming because of this inequality. Because if you are if you have a utility at a specific S1 star and S2 star which is equal to the value, the max-min and the min-max value, then S1 star S2 star is both the min-max and the max-min value. Max-min strategy. So we have shown the necessary condition, that is the only if direction, that if you have a PSNE which is S1 star S2 star, then this equality should hold, and your S1 star S2 star which was a PSNE must also be the min-max strategy and the max-min strategy respectively. Now we will have to show the other way around. Now we are given that this equality holds, where S1 star and S2 star are the max-min and the min-max strategies for players 1 and 2. And let us for our simplicity of notation, let us denote both these equal values with V, let's say. Now what we have, now we know by definition of minima, again the same trick that we are going to use. So if you fix a specific S2 and S1 star is the same, then this by the definition of minima you can always write this. And because this S1 star is a very specific, it's a max-min strategy for player 1, then you can actually write it to be equal to the max over this the strategy of player 1 and min over the strategy of player 2. So S1 star is by definition the max-min strategy. So the equality should hold. And because this is the max-min value, and we know by the what is given in this condition, that is equal to the value V. Now similarly we can use the same thing. So we can use the same argument of U of S1 comma S2 star and we can use the argument of max. So because now we are going to use the other direction, so we are going to show that this is max. So if it is less than or equal to the max with respect to the first quantity here, and you use the same fact that because S2 star is the min-max strategy, then you can use the same argument to show that this is min-max, and because that min-max is also equal to V, so the right hand side becomes V. So you can show that this is also less than or equal to V. But now we also know that this V is equal to U of S1 star comma S2 star. That is given in the very beginning. Now if you just write that down, so what did you get here? S1 star comma S2, and notice that this is for any arbitrary S2. This is going to be this whole implication that we have shown holds for any arbitrary S2 that you pick. So that is going to be greater than or equal to U of S1 star comma S2 star. Right, so therefore the definition of PSNE is essentially this, and from the second implication you can show that this is S2 star, and if the other player is holding on to that strategy, then this is going to be less than or equal to U of S1 star comma S2 star, and this holds for all S2 and this holds for all S1. So if player 1 is deviating from this strategy to any arbitrary S1, it is going to lose out, and if this player 2 is deviating from S2 to S2, it is also going to lose out because its utility is just the negative of it. So that essentially proves the theorem that we started with, that if you have a PSNE, which is a saddle point, it is going to be a saddle point if and only if both this min-max and the max-min value become equal.